Alright, so hello again everyone. So this is another science video lesson, and in this video lesson we will going to talk about earth science. So actually it's not it's earth science, but it's not on the earth. Alright, so if we will talk about something or has something to do with the things that we see outer space. Okay, so let's get right into it. Alright, so this is our topic for this video lesson. So the title of our topic is Life Cycle of a Star. Alright, so if you happen to see, I know you are familiar on this and you'll be able to see this one on the night sky. So there are a lot of them. Actually, there are trillions of them in our galaxy. Alright, not even trillions or more than that. Okay, so there are trillions of stars that are found in our galaxy, and our galaxy is the Milky Way. Alright, so in this particular or in this lesson that we will going to discuss this session, alright, we will try to discover how the stars are formed. Alright, so what are the things needed, alright, what are the things needed and the basic ideas about the formation of stars. Alright, so let's get right into it. Alright, so what is a star? So a star is a glowing gas, alright? So what kind of gas is that? So the gas that is commonly found on stars or in the outer space, in the universe, most common gas found in the universe is hydrogen and helium. So technically speaking, stars are glowing hydrogen and helium, alright? And these things that are found in the universe or in our galaxy, alright, are born in the nebula. Alright, or nebulae. Yeah. Alright, so these are glowing ball of hydrogen gas. Alright, and the temperature, the size, and the mass vary from each and every stars that are found in our galaxy. Not only in our galaxy, but other galaxy as well. Alright, some of them can range or some of them vary in size. Some of them are big, some of them are small. Alright, in terms of mass, some stars are massive and some stars are somehow on average in terms of mass. Alright, some has smaller mass than smaller than usual mass. Okay, so in terms of mass, they vary. Next, also with temperature. Alright, so stars have different colors. So technically speaking, temperature also varies in these objects. Alright, also diameters. Okay, so the diameters of stars is ranging from 450 times smaller than our sun or 1000 times larger than the sun. Alright, so more or less, there are different kinds of stars that we can find out in outer space. All right, so the surface temperature of the stars can range from 3000 degrees, all right, and up to 50,000 degrees Celsius, depending on what color of the stars are we dealing with. All right, so it depends. All right, so the surface temperature of the stars depends on what color of the stars are we dealing with. All right. So, the stars have different colors, alright? So, as I've said earlier, so the colors that we have right here is ranging from blue to white, blue down to white, then down to yellow, alright? So, we have your yellow and down to red. Alright, so the colors of the stars dictate its temperature. Alright, so technically speaking, the warmest color of the star is blue. Alright, it ranges from, in terms of Fahrenheit, it is 50,000 degrees Fahrenheit. And the coolest color of the star is red. Alright, red and somehow yellow, somewhere in between that range. So it has a temperature of 3,000 to 6,000 degrees Fahrenheit. So basically speaking, the color of the color of the star depends. The temperature depends on the color of the stars. All right. So please take note of that. So our sun is 5,500 degrees Celsius. So this is our sun is category M. All right. So category M. So whenever the stars belong to category M, it tells us that the star is somehow not that hot. All right. Not that hot and not that super cool in temperature. All right, so it is a main sequence. All right, in other words. Okay. All right, so brightness. So the brightness of the star is produced. All right, so the light energy that comes from the star is produced via nuclear reaction. So what type of nuclear reaction? We call it nuclear fusion. All right, it is happening inside the core, and this nuclear fusion is because of this nuclear reaction. It is because of the hydrogen combining inside the star's core. Alright, so once the two hydrogen combines, it releases an energy in the form of light energy or radiant energy, and it is scattered outward, alright, away from the star. Alright, so the brightness of the star is measured in terms of magnitude. Alright, so they are measured in terms of magnitude. I think it is in a scale of 1 to 10. Alright, in terms of magnitude. Alright, so that's how the brightness, alright, comes, or that's how brightness is produced, alright? The brightness from the star is the energy produced by the star using its nuclear fusion as the process, okay? Now, how do we measure the brightness of the star? Alright, so we measure it by magnitude, and there are two ways in measuring the magnitude of the star. Alright, number one, we have the apparent magnitude. Alright, so the apparent magnitude is the magnitude used, alright, or this is the brightness as you have seen that object here on Earth. Alright, so this is the description of the brightness of that object from the sky in terms of your reference, which is from Earth. Okay, so that is apparent magnitude. For example, our sun has a greater apparent magnitude than the stars around it. Alright, so as of now, okay, since this is we are in the afternoon, all right? So we are in the afternoon. Sun has a greater apparent magnitude, all right, in the sky, all right, among other objects in the sky. Okay, so when it is nighttime and full moon, the moon itself has a greater apparent magnitude than any stars around it. All right, but the sun and moon, has a low absolute magnitude. So what do we mean by low? What do we mean by absolute magnitude? Absolute magnitude is the brightness of the star, at a standard distance of 10 parsec or 3.2 light year, 32.6 light years. So which means that a brightness of the star under the absolute magnitude, this is the actual, this is the actual brightness of the star, as if you are near the star itself, so if you will compare the absolute magnitude of sun and moon and the Betelgeuse, this which is a star, so if you will compare its absolute magnitude, this has higher absolute magnitude and this has lower absolute magnitude. But in terms of apparent magnitude, Betelgeuse has less apparent magnitude, but sun and moon has greater apparent magnitude because this is what you see on Earth. This is what you see on Earth. So that's how you measure the brightness of the star via whether it is apparent magnitude or absolute magnitude. They are very, very important in measuring this brightness produced by the stars. Now in measuring the brightness of the stars, you can plot them also in a standard graph called Hertzsprung-Russell diagram. So what does the Hertzsprung-Russell diagram tells us? The Hertzsprung-Russell diagram contains data from luminosity of the star and the spectral class of the star, or its color. So the color itself. So as we all know, O is the hottest and M is the coolest color of the star. So it tells us that that luminosity is somehow directly proportional to the color. So the brighter the color, or the brighter the star is, so the brighter the star, the hotter it is. Also with the temperature. So we have red over here. So these are dim stars. So these are dim stars, and dim stars tend to have lesser luminosity, and in terms of temperature, they are they have lower temperature compared to the main sequence over here, which is blue, and the white dwarfs over here. Alright, so basically speaking, the diagram tells us, in short, it tells us that the hotter the star, the higher its luminosity. Alright, so take note that one. Okay, so the hotter the star, the higher its luminosity. Right. Okay, let's discover how the star is formed. Alright, so actually there are two different paths on how stars will form. Alright, or how will its life cycle look like. Alright, now let's start first where all stars are born. Alright, whether it is a massive or average size of star. Alright, so the stars are born in a nebula. Alright, so there are these are objects in the sky. Alright, so these are places in our galaxy where the stars are born and they are created. Alright, so what are the ingredients what are the ingredients needed in order to create a star? Alright, so number one, you need huge cloud of dust. Alright, so probably this is small particles of dust, alright, that is scattered around our galaxy. Alright, next one, we have gas. Alright, so this gas, I am talking about hydrogen gas. Alright, hydrogen gas. Because this gas is abundant in our universe. Right, so there's no other gas, alright, that are abundant in the universe aside from hydrogen. Alright, and gravity. Alright, so gravity is needed in order to form this, what they call protostars or first stars. Alright, so these are first stars. So these protostars are born in the nebula with the action of high gravitational force. Alright, so imagine two hydrogen atoms being fused together by gravity. Alright, so when they fuse together, they will trigger now its sustainable nuclear reaction. Alright, this nuclear reaction is in a form of nuclear fusion. So once this hydrogen combines, alright, once this hydrogen atom combines inside the core of your star, it will continue to generate radiant energy all throughout its lifetime. Alright, so that's how stars are born. So what they need is clouds, gas, and gravitational force. Alright, so there are two ways. Alright, so there are two pathways the stars are born. Alright, so there are stars that are average in size, in mass, and there are stars that are huge, and there are stars that are giant. So these are stars that over 3 times larger than the sun. Alright, so there are several pathways. Alright, so there are several pathways in which the stars are destined to go to. Alright, so there are some that becomes black dwarf in the long run, and there are some that become neutron star, and there are some that became a black hole in the long run. Alright, so later we will discover that one as we go to each path that we have right here. Right, but they start in one region, which is called the nebula. Alright, so we will use the stellarium later to visualize the nebula that we are talking about here. Alright, so this is what the night sky looks like. Alright, so this is this is our galaxy, the Milky Way. Alright, at the center of the Milky Way, there's a black hole on it. So this dark patch that you see here. Alright, so these are this is the black hole that is on the center of our galaxy. Alright, so there are millions or billions of stars all in our galaxy alone. Alright, so we don't know yet in other galaxy how many stars are there. Alright. Alright, so this is another view from another location. So, alright, so this is a truly magnificent thing to see in the night sky. Alright, so these billions of stars scattered around our galaxy. Alright, so let's start first with the first type of stars. So we call these stars are the small stars. Alright, so what are the destiny, or what is the destiny, or what happens to the stars which is lower in mass than our sun, or somehow 2 times larger than our sun? Alright, so what happens to these stars in their life cycle? Alright, let's start first in nebula. So all stars are born in nebula. Okay, so as I've said earlier, what you need there is a globe of gas and dust. alright, that will combine together with the action of gravity. So just to tell you one thing, it's gravity, alright, it's gravity that creates stars, right? And also, it's the same gravity that also kills the star. Okay, so remember the action of gravity here, alright? It is the one of the main forces, alright, needed to kill a star or to create a star. Alright, so let's go to the stage 2. Alright, so once this gas and dust are formed, alright, they now have a central temperature that can sustain thermonuclear fusion. Alright? And the thermonuclear fusion somehow reached over about 15 million degrees centigrade. Alright? It should be hot. Always. It should always be hot. It's because you need to sustain that nuclear fusion. So the higher the temperature, the faster the nuclear fusion. The faster the nuclear fusion can happen. Alright? So if you drop the temperature, the nuclear fusion will cease to stop as well. Alright? So since they have now the sustained thermonuclear fusion in the core, we call it now the protostars. These are the first stars in your system. Okay. Next, the stage 3 is the nuclear reaction will start to fuse hydrogen and they will form helium. Now, if you follow the periodic table of elements, alright, if you follow the periodic table of elements, hydrogen is the number 1, number 2 is helium, number 3 is lithium, so on and then so forth, until you reach iron. I think iron, if I remember it correctly, 26, something like that. Alright, so 26. So until iron, the hydrogen will fuse, and the elements that will be created will fuse and fuse and fuse using nuclear fusion until it reach this element, alright, which will make it unstable. Alright, next, in the stage 4, alright, so in the stage 4, the star begins to release energy, stopping it from contracting, causing it to shine. Alright, so that's the reason why that is the reason why our sun, alright, glows brightly. Alright, it's because it starts to release this energy that is contained over a long period of time, and this particular energy will be in a form of radiant energy. So as of now, alright, our sun is still doing good for the next 2 or 3 billion years. Alright, so before it runs out of fuel. Alright, so by the way, our sun is called a main sequence star. Alright, so this is the middle of this is the mid part, alright, of its lifespan. Alright, so next, the stage 5 will be the stage 5 will be all about the star with one solar mass will remain a main sequence star for about 10 billion years. Alright, so our sun can continue to become a main sequence star around this estimated number of years. Alright, 10 billion years. Alright, until all the hydrogen has been fused to become helium. Now, when all hydrogen becomes a helium, alright, so the helium now will start fusing each other to become the next element. Alright, so in stage 6, helium core starts to contract and nuclear reaction begins to occur in the shell around the core. So, meaning to say, the helium now is starting to combine using the nuclear fusion process. Then, the core is hot enough for the helium to fuse to form carbon. The outer layers begin to expand. Alright? Now, when helium now is starting to form, then it runs out. Then, the lithium also will start to combine. Alright? And it runs out until it forms higher or heavier elements in the long run. Alright, so lithium, what is next to lithium? We have number 5, which is boron, we have carbon, we have nitrogen, so on and then so forth, until you reach iron. Now, once the stars are fusing helium and other elements on its core, it starts to expand outward. It starts to expand outward, and once it expands outward, it grows in size. It is now called a red giant. All right, so that is the process there. Okay, next one. Next is the stage 8 is the helium. All right, when the helium core runs out. All right, so if the helium core runs out, these stars, the gases outside this star that you have right here, the one that you see on the picture, will try to drift away from the surface. All right, it will try to drift away or be emitted away from the surface of the star, thus producing a glow of light, all right, around it. We called it the planetary nebula. All right, so these are the gases that once part of the surface of the star that drifts away from the surface, right? So that drifts away from the surface and produces this glow that you have right here. All right, so this thing that you have right here is called planetary nebula. Okay. Next, on stage 9, alright, on stage 9, when it becomes a planetary nebula, so as you can see, there is no explosion that happened. Alright, so there's no supernova. Instead, once all the outer layers has been drifted away from the core, alright, the remaining part or the remaining core of the star, alright, will which is still hotter, alright. Alright, so in terms of temperature, it is still high. Okay, we call it now white dwarf. Alright, in terms of luminosity, this is category O. Alright, so this is under the classification of O, which means it has a higher temperature, but in terms of luminosity, it is somehow lower. Alright, it is somehow lower. So this is a star which has higher temperature, but it is dim. Alright, now as time passes by, it will cool down. Alright, cool down and dims. Alright, so when it does, it stops shining and it become now your white dwarf. Alright, so this is the destiny of our sun. Alright, this is the destiny of the sun. So the sun eventually, after billion years from now, it will become a white dwarf and eventually become a black dwarf. So hopefully, if we manage to get away from Earth and find another planet to live in, alright, so hopefully by that time, there will be no humans here on Earth. Alright, so there will be no humans here on Earth. We will now be able to colonize other planets. Alright, so that is the black dwarf. That is the last stage of this small average size stars. Alright, so let's go now to the path number 2, which is the massive stars. Alright, so the massive stars. So what makes these massive stars different from normal or an average stars? They have greater mass. Alright, some of them shines brightly. Alright, shines brightly, and once they shine brightly, they have a temperature that is far greater than the average stars. Alright, so basically those are the characteristics of massive stars. And massive stars, alright, so one sad truth about massive stars is they have shorter lifespan. Alright, they have shorter lifespan compared to their cousin, the average stars. Alright, why do they have shorter lifespan? Okay, why do they have shorter lifespan? It's because of one thing. They consume all their fuel faster. Alright, they consume their fuel, which is the hydrogen, faster. They combine it faster, alright, at higher rate. Then it produce a lot of radiant energy in the process. So therefore, if you combine this hydrogen atom in a higher rate or faster rate, okay, so what happens is you run out immediately of fuel. So what will happen is you will force your star to create more and more elements inside its core in a faster rate, alright, compared to your average size stars. Alright, so this is a double-edged sword on these stars that you have right here. Alright, they will fuse their hydrogen faster, but in an expense of shorter lifespan. Okay. Alright, so massive stars are stars that is categorized, which is 3 times higher or greater than the sun. Alright, and some of them are 50 times brighter than the sun. or not brighter, greater in mass, in terms of mass, than the sun. All right, so what are those stars that we have right there? So these are the red giants. All right, we have the blue star that are found in Sirius constellation, something like that. All right, so there are many massive stars in our galaxy. All right, so one of those is Betelgeuse. All right, so okay. And we have Canis Major, yan, found in the Canis Major constellation. We have Uis-Scuti, UI-Scuti. So Scuti is found in the Scutum constellation. Okay, so and there are more massive stars that are found in our galaxy. Alright, next one. Okay, so basically it's the same thing as the average star. So it starts with nebula, gas and dust will be formed via gravitational force. And in the stage 2, alright, also massive stars have also their main sequence stage. Alright? So massive stars also have this stage that we have right here, similar to our sun. Alright. Now, as the star continues to shine, alright, throughout its lifetime, alright, its hydrogen supply will be consumed all throughout. And it starts to form the helium. Okay? It starts to form the helium. But in a small star, it takes billion years. Alright? It takes billion years to do this. Alright? It takes billion years to do this. But in a massive star, it takes only million years to do this one. Alright? So that's the difference. Alright? So that's the stage 2. Now stage 3, just like your average star, once it forms once it starts to form an element, all right, inside the star, or heavier elements, all right, like lithium, carbon, oxygen, nitrogen, inside the star, it will likely to expand, but compared to your average stars, the expansion of this one is much bigger than the average star. Alright? So it is now called a red supergiant. Alright? So it's the same thing. Alright? Why are the stars, alright, like this one, is increasing in size? It's because it starts expanding due to the formation of elements inside the core of its core. Yeah. Inside its core. Alright, so it starts to expand outward. Alright? And okay, just like the sun, when it die, alright, so if our sun undergoes supernova, alright, if the sun undergoes supernova, okay, or when it becomes a red giant, probably it will swallow the Earth, number 1, that's one theory. And number 2, the Earth will flow or fly away on its present orbit, because once the star becomes a red giant, its gravitational force becomes weak. So the Earth's orbit will be adjusted, alright, in the long run. Okay, so we don't know what will happen. Okay, so next one. Stage 4. In the next million years, alright, so for the next million years, the nuclear reaction will continue to create these elements, heavier and heavier elements, alright, including the iron that we are talking about. Okay, and this is it. Alright, it starts from hydrogen, then it forms the helium, then it forms the element next to helium, so on and then so forth. Alright, so as it continue and then continue until it reach this one. Alright, the iron will make the star unstable. Right? So once it makes it unstable, it will undergo supernova. All the elements under this periodic table, under this area, all right, all the elements under this area will be, all right, will be the byproduct of supernova. Okay, it will be the byproduct of the supernova in the process. Okay, so basically speaking, all the atoms inside our body are part of a dying star, right? So the calcium, the oxygen, the nitrogen, the phosphorus inside our body are once part of a dying star, all right? So stage 5, we have supernova. Unlike the average stars, in massive stars they undergo supernova. This is a cataclysmic explosion, all right? This is a cataclysmic explosion on the universe. All right, this is one of the magnificent thing to see on the universe. All right, although it is a violent explosion. All right, so the shockwave. All right, the shockwave of the explosion blows all the material away from the core. Right, so blows all the material, so it scatters all the material, the iron, all the elements, all right, away from the core or away from the center of this explosion. Right, so that's the reason why, all right, that's the reason why our sun is born. Okay, and some planets are also born in this way. All right, so that's the supernova. Okay. So, okay, so be careful when you wish on a star because who knows that the star is already dead because light travels at 3 times 10 times 10 raised to 8 meters per second. So, probably before it reaches you, all right, before the light reaches you, we assume that the star is already dead. Okay, so because speed of light is somehow not that fast, okay, to reach on our place, all right, as fast as it can. Okay, so okay, so please okay, please this is a warning to those who wish upon the stars, all right, so okay, maybe the stars is dead just like your dreams. Okay, so be careful, be careful. Okay. Right, next, the stage 6, alright, so after the stars continue to cook these elements inside and undergo supernova, alright, the stage 6 depends on what kind of star it is. Alright, if the star is highly massive, it becomes a black hole. And when the stars is somehow 3 times larger than the sun, it becomes a neutron star. A neutron star is a very dense star, alright. So let's put some reference here. Okay, neutron star is a size of is the same size as an Earth. All right, is the same size as Earth. Okay, so that's the neutron star. But compared to Earth, neutron star is very dense. So meaning to say, it is very compact. All right, so it's very compact. So it creates this high gravity environment. Alright, so it creates this high gravity environment because it is very dense. Alright, so this is the neutron star. So the stars that explode using that undergo supernova will become a neutron star, and it will become a neutron star for the next billion years. Alright, so and some stars became a black hole, which this is a monstrosity these are monsters in the universe that eats everything on its path. All right, it eats everything on its path. No matter can escape when it is inside the black hole. All right, basically the black hole distorts the space-time. All right, the space-time fabric, okay, in the universe. Okay, so whenever there's a black hole, it affects how the gravity, all right, acts, okay, on the objects around it. Okay, so even light cannot escape a black hole. All right, so that is the thing there. Okay, so recently, guys, we happen to see a picture of a black hole. All right, so a very impossible that's a very impossible thing to do, but we humans tend to do it. All right, this is one greatest achievement of humanity. We have a picture now of a black hole. All right, a clear picture of a black hole that will tell us how black hole behaves. All right, next one. All right, so to end up our session, all right, before we end up our session, let's have a quick summary of everything that you have found in this session that we have in this video lesson. Okay, number 1 is nebula. All right, so let me repeat. Nebula is a cloud of gas and dust in space. These are considered to be the birthplace of stars. Alright, so please take note of that one. So the stars are not born anywhere else in the universe except in nebula. Alright, so I will try my best later to show you the nebula in the stellarium. So what are the available nebula that are found in the stellarium? Alright, next one. There are types of nebula which is categorized according to its how it behaves. So we have an emission nebula. This nebula, based on its name, it emits, alright, it emits light at different wavelengths. Alright, it emits light. And planetary nebula is also known as an emission nebula. Alright, so it emits light. So basically, a star, alright, a nebula which is called an emission nebula emits these different wavelengths. That's the reason why it gives it its signature color. Alright, next one, we have the reflection nebula. So from the word itself, reflection, it reflects the light from the surrounding stars. Alright, in this particular nebula. Alright, so we have dark nebula. Alright, so what it does is it absorbs all the light from the surrounding stars. Right, so it absorbs all this light. So that is why it is called dark nebula. So we can say that if you happen to look at the picture of dark nebula in the Google Images, alright, you can say that it really absorbs this light around it. Alright, so this is nebula. Okay. Alright, so a star is an object in the universe, in outer space. These are luminous globe of gas, or let me be specific, we call it hydrogen gas. Alright, that sustain its, that produce its own heat and light via nuclear fusion. So take note of that one, nuclear fusion. Alright, so they are born in the nebula, and some of them ranges from 2,000 degrees Celsius and 30,000 degrees Celsius surface temperature. Okay, so the corresponding color is from red to blue to white. Alright, so the colors depends on the temperature of the star, so they are directly proportional. Alright, next one, the brightest stars have 100 times massive, or it is 100 times massive than our sun. Alright, so basically just take note of that. Okay, the mass of the stars is directly proportional on how bright it is. Okay, so that's the fifth bullet. And okay, and massive stars, okay, live less than a million years, right? And they explode in a supernova process. Okay, so massive stars have a lifespan of, or they have a shorter lifespan compared to average stars. Okay. Alright, so faintest stars are called red dwarfs. Alright, so red dwarfs are, I think it is a similar size of a Jupiter, something like that. Okay, so, or much smaller than Jupiter. Okay, so these are red dwarfs. These are cool stars. Okay, these are cool stars. So it has a surface temperature of 3,000 degrees Celsius, something like that. Okay, and this red dwarfs has a longer lifespan compared to your massive stars. All right, so the blue stars. All right. Okay, so alright, so we have the red giant. So these are large bright star with cool surface. Alright, so these are bright stars, but it has cool surface. These are red giant. So when it runs out, when a star runs out of its hydrogen fuel, it becomes a red giant. Okay, it expands. Alright, it expands outward to become a red giant. Okay, sometimes the diameters of the stars reaches around 100,000 or 1,000 times the diameter of the sun. Alright, and the luminosity is far greater than our sun, 1 million times greater than the sun. Alright, so that is the red giant. So we have this super red giant, which is much larger than a normal or usual red giant. Alright, so this is what the red giant looks like compared to our Earth and compared to the sun. Okay, so eventually the sun will undergo the same process. Alright, it will become a red giant 2 billion years from now. Okay, so one example of red giant found in the in our galaxy is called the Uisqt. Alright, so this is what the sun looks like. Alright, so this is a hypergiant. Alright, so this is a hypergiant, much larger than the supergiant. Okay? Next one, the red dwarf. So as I've said earlier, these are cool and faint small star. Alright, so they have a longer lifespan compared to the massive stars. Right. Next one, the white dwarf are very small and they have a temperature which is under category O, which is 50,000 degrees Celsius, something like that, or degrees Fahrenheit. Alright, and white dwarfs has a mass similar to the sun, so it has compared to the sun, they are the same in terms of mass. Alright, it has a smaller diameter. Alright, it has smaller diameter and approximately the size of the Earth, or the diameter of the Earth. Right, it has a surface temperature of 8,000 degrees. Right, it is hot in here. Okay, and the luminosity of this white dwarf are 1% of the sun. Alright, so some of them are less than. Alright, so white dwarfs are... Okay, basically white dwarfs are shrunken remains of normal stars. Alright, so our sun will become a white dwarf in the long run after it expends all of its fuel. Alright, that's the white dwarf. Okay, so this is a Sirius, alright, so this is a Sirius star found in Canis Major constellation. So this is the white dwarf that you can find near that star. Alright, so white dwarf. Dwarf. Okay, so next one. Okay, so the supernova is the process, or this is an explosive death, alright, of massive stars. Alright, so it creates a lot. It creates a brightness much brighter than the sun, 100 million, alright, times the sun. Okay, much brighter than the sun. Okay, so sometimes supernova leaves behind neutron stars or even black holes in the process. Alright, so... Okay, so this is the supernova. Okay, so all the materials that are created inside the stars, all the elements are created in this particular fashion, which is the supernova. Okay, the iron, the uranium, the iodine, alright, the oxygen, alright, all the elements are scattered outward and it becomes a future planet, or even it becomes another star in the long run. Right? So it is probably thought that the supernova is where the hydrogen, all the hydrogen, alright, in the universe came from. Alright, so the first supernova created that one. Okay, so we have the neutron stars. So the neutron stars are very dense. Okay. Okay, so it is very dense. So it has a gravity much greater than any planet. Okay, so it has a gravity which is it has a gravity much less than the black hole. All right, so that is the neutron stars. All right, it produce these radio waves, and it has its own magnetic field. All right, so that's how amazing these objects here. Okay, so we call it the neutron stars. Right, so these are the artist rendition of neutron stars. All right, so although some astronomers already seen a neutron stars, but they cannot. This is how it looks like when you visualize it. Okay. All right, so we have the black holes. All right, so the black holes are the ultimate end of all massive stars. All right. Now the black holes are very different. All right, so they do not shine. All right, they do not shine. That's the reason why it is called black hole. And the density inside the black hole is unknown still. All right, as of this time. All right, and its gravitational pull is much greater than the neutron star. All right, so in short, even light cannot escape from a black hole. All right, so if a star is nearby the black hole, it will swallow it. All right, it will swallow it step by step. All right, so basically black holes are the monsters in the universe. All right, so that's how great these black holes are. So this is the black hole found in the movie Interstellar. Alright, so if you remember that movie, this is the planet where the astronauts went, and it has a day. Alright, it has a time there, which is 1 day on that planet is equivalent to 7 years here on Earth. Okay, Earth years. Yeah. Okay, so meaning to say that the black hole beside it, okay, influences the gravity, all right, influences the gravity that acts on this planet. So that is why it is, all right, it is the day here is much slower, all right, much slower compared to Earth. Okay. So that is on the Interstellar. This is only a fictional. This is only fictional, guys. Yeah. All right. So this is a picture of the black hole, which is it happened in 2019, something like that. So these are the glowing gases entering the event horizon. All right. So these are the glowing gases. Okay. So okay, so before I end up, so just a quick view of what will happen to different stars with different mass. All right, so the stars with 0.08 to 8 times the mass of the sun will become white dwarf. All right, so this is the destiny of the sun. Okay, next one, the stars with 8 to 20 times the mass of the sun will become a neutron star. Right? And finally, the stars with more than 20 times the mass of the sun, which is supermassive stars, will become a black hole in the long run. Alright, so with that, so with that, let's go now to the Stellario. Okay, so all right, so let's use this Stellario. All right, so let's try to remove the atmosphere. So you can download the Stellarium on their website. So it is 225 MB in file size. All right, so pretty large. All right, so pretty large, but okay, so it's a good thing to use if you want to become an astronomer in the future. This is a very good guide, all right? So let's remove the atmosphere. So okay, so today is 2 o'clock, so there is still sunlight around, so we can remove that one here. Okay, so as you can see, this is what the night sky looks like without the atmosphere. All right, so without the atmosphere itself, so that's how it looks like. So you can set the location here. All right, so you can set the location and you can find something here. All right, so let's find some objects here. Example, the pillars of creation, which is called the Eagle Nebula. All right, so the Eagle Nebula. All right, nebula. All right, so there you go. All right, so it's still there at the bottom. Okay, so we will rise it up. Okay. Okay, so there you go. That's the Eagle Nebula. So if we will going to zoom in, right, on that direction. Alright, so there you go. That's the Eagle Nebula. So just zoom it further. Alright, so there you go. So as you can see, there are a lot of stars born on that region. Alright, so it is the birthplace, basically, of all the stars that we know in this universe. Alright, in this galaxy. Alright, so not only the Eagle Nebula, so we have also a very familiar one. So we have it right here. Right, so we have, let's find it. So we have Orion Nebula. Okay, so we have the Orion Nebula. So it is still underneath. Okay, so let's find it again. Okay, now you can use codes. All right, you can use codes placed or used by designated by International Astronomical Union. Alright, so later we will use that codes. Alright, so let us find first this Orion Nebula. Alright, so there you go. That's the Orion Nebula. And if we will zoom in, alright, so that's how magnificent it is. Or okay, so this is a pre-recorded picture, but I don't know if it still look like as of today. So okay, so that's it. That's the Orion Nebula. So there's another one which is called the Andromeda Nebula. Okay, so there you go. Alright, so that's the Andromeda Nebula. Okay, so this is the nearest galaxy, alright, on Earth. Okay, so we have here another M110. So 30 billion years from now, or something like that, this galaxy will collide to our Milky Way. So basically, this is also a nebula. All right. On it, there are stars that are born inside. All right. So let's try to find other stuffs here on Stellarium. All right. So that's how good this application is. So you just download it on their website. All right. So okay. So we find Okay, let's find another one. So let's find some planetary nebula. For example, NGC. Okay, NGC 6543. Alright, so there you go. There's a query there. Alright, so just click it. Then, okay. So just, okay, just wait for it to rise. Okay, so some... Okay, so there you go. Okay, that's the one that we are looking for. Okay, so we zoom in. Alright, so it is very small. It is very small because it is very far. Alright, compared to other nebula that we have encountered a while ago. Okay. So by the way, this is the magnitude. Alright, so this is the color index. Alright, so if we zoom in, alright, so it has a greater, okay, so it has a greater image, or it has a good image. Alright, so this is the nebula. This is a planetary nebula. Alright, so this is a planetary nebula. Okay, so last one. So we'll try to find okay, let's try to find something. Okay, like okay, so let's try to find something like this one. So 3C273. Alright, so 3C. Right, so 3C273. Right, so there's no, ayun. So there's, okay, so this is a unknown, this is an unknown object here. Okay, so this is a quasar. Alright, so this is a quasar. Okay, so a quasar is an object that emits this radio wave on outer space. So basically, this is how this program describe a quasar. So okay, you cannot see the good image of a quasar here because it's somehow very far, right? So okay, so I think that's it. Right, so we have here the Arcturus, another star which is under a red giant stars. All right, so if we take a look at that Arcturus, okay, so this is a giant star. Okay, there you go. So that's the Arcturus. Alright, so you can use this stellarium, guys, in order for you to find things in the night sky. Okay, so it will be a great guide for you to find a lot of things. Alright, discover a lot of things in the sky. Alright, so with that, that ends up our video session. Alright, video lesson rather, and today's session. Okay, so if you learned something from the video, so hit the thumbs up. So the link on how to download the Stellarium or how to have the copy of Stellarium is on the comments or on the description of this video. Alright, and okay, so if you learned something from this video, just hit thumbs up. Alright, and just don't forget to subscribe to my channel and click also the notification bell if you want more videos like this one to be added to the future in the future. Alright, so if you have questions, write it down in the comments, alright, section of this video. And if you want to suggest some videos that you want me to create in the future, just write it there in the comment section. Alright, so I believe that's it. So let's see each other next time, and until to the next video. Goodbye, guys.